17. Explain and draw sketch A, giving example of each type. Distinguish between periodic and harmonic motion. So let us understand periodic and harmonic motion. Okay, so I'm writing periodic motion. So when a body, okay, repeats its motion over and over again after regular time intervals, then its motion, okay, is called periodic motion. So we have this for periodic motion. Now let us understand with reference to the example. Okay, so 1, motion of the hands clock is periodic. Okay, so this is periodic. Let's say this is the hand clock or hand watch. Okay, so there are 3 needles. So we have this, I'm drawing it roughly. Now what we find, each of these needles, okay, they repeat their motion over and over, okay, after regular interval of time. So we find this. Each of these needles, they repeat their motion over and over after a regular interval of time. So this kind of motion is called periodic motion. Okay. 2, motion of the moon around the earth is periodic. Okay, this is periodic motion. Now let us understand harmonic motion. Okay, harmonic motion or oscillatory. Okay, oscillatory motion. So we have this. Now if the body, okay, if the body moves back and forth repeatedly, so if the body moves back and forth repeatedly about its mean position, clear, its motion is said to be oscillatory or vibratory or harmonic motion. Sorry. So we need to understand this. Okay, we need to understand this. Now let us understand what is back and forth. Okay, let's say we have a simple pendulum. Okay, and it is at rest. So this is the rest position, or it is also called mean position or equilibrium position. And when the pendulum is displaced by small angle theta, okay, so this is the extreme position towards right, okay, of the equilibrium position or mean position. So we find this, okay, we find pendulum at this position, and finally from this extreme position it returns to the mean position, and from mean position it again reaches this extreme position, okay, this is extreme position towards left of the mean position. So this is extreme position, and from this extreme position it finally returns to the mean position. So we find simple pendulum, okay, is having back and forth repeatedly about its mean position. So such type of motion is called harmonic, oscillatory, or vibratory motion, okay. And the example of harmonic motion, okay, so I'm writing over here example, clear. So this is one of the example. Next example is, let's say we have a mass spring system, okay, this is mass m and this is spring with spring constant k, okay. So we have this and we have a frictionless table, okay. Now this position corresponds to the rest position or equilibrium position. Now when we apply force, external force, okay, in this direction, then what we find is that, okay, due to external force the spring gets elongated. So we have this, yeah, the spring gets elongated, and let x be the extension produced in the spring. Now when we release external force, then due to the restoring force, okay, so we have restoring force acting inward, the spring moves back and forth about this equilibrium position, okay, this is the equilibrium or this is the mean position, so we have this, clear. So it moves back and forth about its equilibrium position. So such type of motion is called harmonic motion. So I'm writing the example, okay, let's say oscillation of mass spring system. So this is an example, so I can take this as an example also, okay. And we need to understand, okay, that every oscillatory, okay, motion is necessarily, okay, periodic. It is necessarily periodic. Clear? Why? Because it is repeated at regular interval of time. So we need to note this, okay? Every periodic motion need not, okay, it is not necessary, need not be oscillatory. So this is to be noted, okay. Example, Earth completes Earth completes one revolution. So let me write over here. One revolution, clear, around the sun in 1 year. But it is not, okay, it is not to and fro, that is back and forth, okay. It is not to and fro. So this is to be noted. It is not to and fro, back and forth motion about any mean position. So we have this. Hence the motion is periodic but not oscillatory. Hence the motion is periodic, okay. The motion is periodic but not oscillatory. So we have this, or harmonic. So we have this. Now let us look for 17b. Justify that sine theta and cos theta are periodic functions. So periodic function, okay. Let me write in this way. What are periodic function? So what is the condition for function to be periodic, okay. So let us say this. So let me write in this way, okay. Periodic function. So we are going to understand this. Now let us consider function, okay. Let's understand with this concept, okay. Consider a function f theta, okay, satisfying, so it is satisfying the property f theta plus t, equals f theta. So if the function is satisfying this property, then the function, okay, we are taking remains same, okay. So I'm writing the function f, okay, we are taking remains same when the argument, okay, when the argument, now what is argument, okay, of the function. So we need to understand this, okay. So I'm writing over here So this is the independent, okay? Independent variable or argument, okay? So we can define or understand argument in this way of function is a value, okay? It is a value provided to obtain or find, okay? Find the function. So this is to be noted, okay? So we have this, clear? So I'm writing over here, clear? Argument is increased, okay? So it is increased or decreased, okay? By an integral, okay? Multiple, integral multiple of t, okay? So we have this for all values of theta. So we have this. So function satisfying this property, okay, is said to be periodic, okay? So I'm writing over here the function f. So we are taking function f, okay? F satisfying this property, okay, is said to be periodic. So it is said to be periodic, having period, okay, t. So we have this, okay? And so this is continued, okay? Continue. Trigonometric function, okay? So I'm writing, we know sine theta and cos theta are trigonometric function, okay? Trigonometric function sine theta and cos theta, okay? These two, cos theta, are periodic function, okay? Are periodic function, periodic with period. So it has period with period twice pi. So we have this. So we use this concept or property, okay? Therefore, we can write sine theta plus twice pi equals sine theta, and cos theta plus twice pi equals cos theta. So we have this, clear? So we are asked to justify that sine theta and cos theta are periodic function. So what we find, sine theta and cos theta satisfies this property, okay? So it is, or they are periodic function. So we have this. Now next, 17c, nature of kinetic and potential energy in harmonic motion. And remember, we are asked to explain and draw sketch, okay? So 17c, nature of kinetic and potential energy in harmonic motion. So question 17C, okay? Nature and sketch. So for harmonic motion, okay? So let me draw over here. So this is energy, clear? And we have displacement along the horizontal axis, okay? So we have this. Now what we find, let's say this is the extreme position, okay? I'm taking it roughly. Okay, so we have this. Let's say this is plus A, maximum amplitude, okay? And this is minus A. So we have this. So I'm writing this corresponds to, so let me write in this way, okay? X equals plus A, maximum amplitude. And here we have X equals minus A. So we have this. Now what we find at X equals 0, okay? So this corresponds to the mean position. Okay, this corresponds to mean position. So in this case, kinetic energy, this is half K, okay, times square of the amplitude. So we have this. So kinetic energy is maximum, okay, at the mean position. And potential energy, so let's say potential energy is represented by U. So this is 0. So potential energy is 0. So we have this. Clear? And at extreme position, okay? Extreme position, that is X corresponds to plus minus A. So what we have kinetic energy equals 0 and potential energy equals half K times square of the amplitude. So I'm using two colors, okay? So what we find is that the nature of the graph is like this, okay? Is like this. I'm drawing it roughly, okay? So it is like something like this. Okay, let me make this. So we have this. So this is kinetic energy. Okay. And what about potential energy? So we know at mean position, potential energy is 0. So we have this. So it starts like this. Okay. And at extreme position, it is maximum. Okay. So we find this. So this corresponds to the extreme position. So we have this. Clear? So this is for potential energy. This is for potential energy. So I'm writing in this way, potential energy, and this is kinetic energy. So we have this, and when we add it, okay, then we get total energy, okay? Let me draw in this way. So we get total energy. So we have this. So this line, okay, this is the horizontal line. This is a horizontal line, okay, parallel to the displacement. Okay, this. So we have this. So we have this, okay. Now what do you find? This straight line, horizontal straight line, represent total energy, okay, which is sum of kinetic and potential. So we have this. Clear? We have this. Now, next, okay, the sketch of energy with time. So let's see the sketch of energy with time. So time t and energy, okay. So we have this, and we know when we add kinetic and potential, then we get total energy. So we have this. So this is to be noted, okay. So what do you find? So I'm drawing in this way at first. Total energy is constant. Okay, so we have this. So this is total energy, sum of kinetic and potential. So we have this. And what we have kinetic energy, K equals half m omega square a square sine square omega t plus phi. And we have potential energy, half m omega square a square cos square omega t plus phi. So I'm writing in this way, okay. So we find sine in in kinetic energy, and it is square, okay. So what we get? We get this. We have sine square in kinetic energy. So we have kinetic energy in term of sine, okay. So we have sine square. So keep in mind. And since we have a square, so we get this, okay. We don't get negative cycle because we have a square, keep in mind. So this is kinetic energy. So we have this. And we have potential energy in term of cos square, okay. So we have cos square for potential energy. So we know we can represent potential energy in this way, okay. I'm drawing it roughly. So we have this. Clear? So we have this. So this is potential energy. Clear? This is potential energy. And let me draw a solid line, okay. This horizontal straight line gives the total energy.